Hello, Rachel. My name is Jakob. I think that's all you need to know. Can you see my screen now?
Yes, I can.
Yes. And thank you so much for the invitation to Mohammed and Rachel for this opportunity. I've been looking forward like a child on Christmas Eve to this opportunity.
Oh, I love that.
Yeah, no, that's true. Um, As you may notice, English is not my first language, so please bear with me when I struggle to express myself. And I have arranged with Rachel and Mohammed to interrupt me whenever anything needs clarifying. Also, you are welcome to ask questions in the chat or raise your hand. I won't be able to see while I'm talking, but I'll try and make some short pauses as we go along. And Mohammed and Rachel, you can stop me if anything needs clarification. Otherwise, I just say I'm a medical doctor. That's my profession. I've spent most of my career working in patient safety and healthcare improvement, and I'm especially interested in statistical process control. I've done some work with Mohammed, and a year ago or so, he sent me an article, said, read this. This is about a new statistical process control chart, as if we didn't have enough already. It took me half a year before I read it, but then I was hooked because this new chart claims to be able to replace or at least support many of the traditional SPC charts. And what a relief if we could only need to learn one SPC chart in the future. Also, I want to say before I start that while preparing, I have assumed that you are all familiar with statistical process control and that you have some experience with R. If that's not you, please, you're welcome to stay. You might get curious and you might want to learn statistical process control. You might want to learn R, and there are many opportunities for that for you. So this is my agenda. I'll start with a short presentation, just back to basics, statistical process control in a nutshell. I'll say a few words about the I prime chart. I urge you to read the original paper about it to really understand what it's for. But most of the time, I'll demonstrate how to construct I prime charts using a package, an R package called PP charts. It stands for process behavior charts that I have developed. It's still in early development. You'll find it on GitHub. And I'll simply go through that, demonstrating its abilities, and hope that some of you will take on the challenge and do a thorough testing of this package and also of the I chart, the I prime chart in particular. It's early days, and I think the I prime chart is very promising. I'm reluctant to say that I would simply replace all the other charts with the I prime chart at the moment, but it may very well be the case in the future. So let's get going. Any questions or comment at the moment, Rachel, Mohammed?
No, you go ahead.
I go ahead. As most of you know, this is the standard control chart. It's a plot of data over time. On the x-axis, you have the time, and each dot is a measurement or a count of something that you want to follow over time. There are 3 lines in the control chart. The center line is the mean of all the measurements or the counts, and then we have a lower and an upper control limit. And the control limits, they surround what we expect to be the natural variation, the so-called common cause variation in data. So in a purely random process, we would expect future data points to cluster around the center line and sometimes move a little away, but very rarely to position themselves outside of the control limits. If any data point moves outside of a control limit, we regard this as a special cause. And please bear in mind that special causes are not proof that anything in the process has changed. It's merely a signal, a signal to go investigate whether there is a special explanation for this data point. We talk about two types of variation: common cause and special cause variation. I expect you have a good grasp of these already. But common cause variation is the natural variation that is always present in anything we might measure or count. We know that if we measure the same thing twice, we will not get the same results. But even if data are different, it doesn't mean that these data points come from different processes. You can think of a die, throw a die, and you throw a die 2 or 3 times, and you would not expect to get the same results. You would expect to get results from 1 to 6. That would be the normal natural variation in a die. But if you throw a die and you suddenly get a 7 or an 8, you know this is special. This is not part of the usual process, and we call that a special cause. And that's the whole idea of statistical process control. That is to tell common cause from special cause variation, to know when to investigate whether a process has changed or not. And this is an example of a special cause. We have daily measures of blood pressure, and we see there's one data point that falls below the lower control limit. This is a special cause. So the chart is telling us that there is a reason to believe that this data point has been influenced by something else that affects all the other data points. So maybe we could learn something from this data point, a special cause. There are other tests to employ on a control chart than just data points outside the control limits. We won't go into that today. That could be for another day. The problem with SPC is that there are lots of control charts for different types of data. And these are just a handful of the most used control charts. There are literally hundreds of different control chart types out there. What is common for all control charts is how to calculate the control limits. The control limits are always, or almost always, positions at 3 standard deviations below and above the center line. And the center line is the average or the median of the process. So the trick is, how do we calculate SD, standard deviation? And standard deviation, it's not the standard deviation of all the data points. It's a standard deviation, the assumed standard deviation within subgroups, that is within each data point we use to calculate the control limits. And depending on the type of data, whether we have counts or rates or proportions or measurements, there are different formulas for calculating SD. And this is one of the things that makes SPC confusing, not the least for beginners. And also, these different types of control charts, they expect data to behave in different ways. We expect data to come from a Poisson or binomial or normal distribution and so on. This is a barrier for using SPC. I'd say one thing about the eye chart for individual measurements. The eye chart is considered the Swiss Army knife of SPC. It was originally designed for individual measurements, for example, blood pressure, individual measurements of blood pressure. But it has been shown to be useful for almost any type of data. It's very robust for deviations from distributional assumptions, and it also works well for count data and aggregated measurements. And some even recommend the eye chart as the only chart you need. And I know that in the NHS especially in the plotted dots package, the eye chart is, as far as I know, the only chart available. And the eye chart really works for most situations. However, the eye chart is not good when you have varying subgroup sizes. That is when the number of patients vary considerably from measurement to measurement. You may get false results from your analysis because the eye chart is not able to take that into account. Here comes the eye prime chart. The eye prime chart is designed to take subgroup sizes into account. And doing that, the eye chart has the potential to replace almost any other type of control chart because it works for count data and for measurement data, and it accounts for the sizes of the subgroups or for example, the number of patients in each data point. Mohammed and I, together with the inventor of the eye chart, Wayne Taylor, we are working on a paper on the eye prime chart, and we have done some serious testing and found, first of all, that the eye prime chart matches the original eye chart when we don't consider subgroups. And if we consider subgroups, the eye prime chart produces wavy control limits as we would expect. Also, we found that when we use the eye prime chart for count data that we would normally present in P or U or C charts, the control limits are often very, very close to that of the original chart. So that's promising. So the only problem with eye prime charts, as I see it so far, is that to calculate the control limits is a bit more involved than calculating control limits for the traditional eye chart. The central point is this one. That is how to calculate the standard deviation, the within subgroup standard deviation. We have to use this formula. If you look at the numerator, actually this is the moving range, the same value as we use for the traditional eye chart, but then we divide by a factor that depends on the size of the denominators. If the denominators are 1, this simplifies to the same formula we use for traditional eye charts. Since we are in the R community, we can leave these calculations to R or other types of statistical software, and we should be good to go. I have worked on a package, an R package called PB charts, process behavior charts. It's available on GitHub, and you can install it using this command, and you can load it using the usual library command. And for the rest of this session, I will demonstrate how to use this PB charts package. So any questions so far?
No, we've got no questions so far, so go ahead.
No questions. That may be a good sign or a bad sign.
It's a good sign. Oh, actually, we do have a hand up. I've just said that, and
great.
I do have a hand up. Is Siva?
One of the things
I can't quite
Sorry,
hear you.
I can't hear you.
Can you hear me now?
Yeah,
I can hear
perfect.
you, yes.
Yeah. Okay. Sorry. You can see me as well. Hi. Quick question, Doctor. I think one of the problems that we find with all these charts is actually where to use it and when to use it. And there are different types of chart. If you can, while you explain the demo, could you kindly give us an explanation of when and where to use it as well? That'd be really helpful, Doctor.
Do you mean when and where to use the I prime chart or
That's
all
right.
the
Yes.
Yeah.
Any scenarios, if you can give us.
Yes.
A bit.
The promise is that I prime charts will be able to be a substitute for the usual charts like P charts, C charts, U charts, X bar charts, and I charts. I think it's too early to say that is true, but it may very well be the case in the future that we will simply use the I prime chart for everything. I think we could discuss that also at the end of this session,
Yeah, sure.
when to use these I prime charts. But for the sake of this presentation, I will use I prime charts. I will demonstrate the use of I prime charts for all types of data. Is that okay?
Thank you, Doctor. Thank you.
There's just one more question that somebody's popped
Yes.
onto Menti. So if I just share that with you, so in case it's easier to answer that now and not wait till the end. So somebody says they've used p-charts to account for over dispersion in proportions or rates. And this person is saying, you are describing the I as similar to Laney's P. Is the assumption over dispersion is related only to subgroup size? Does that make sense, or should I actually share my screen so you can read it again?
It makes painful sense. It's a difficult question. I think over dispersion has very much to do with subgroup size, but I think over dispersion and under dispersion, for that sake, happens whenever your data does not behave as expected. The major reason for data not behaving as expected is that data do not come from a binomial distribution, but that only becomes visible when the subgroup sizes are large. In fact, even if the subgroup sizes are small, your data may not be truly binomially distributed. But that only becomes visible when the subgroup sizes are large. Mohammed, help me.
No, Jakob, I think it's an important question, but I think for now, because you're trying to introduce the basic idea, let's get that on the table, and we'll pick that up. It could be a question we ask. It may need further investigation, actually.
Yes, that's very good. Okay.
Okay.
So can you see this is my R Studio. I can zoom in if you like, but if this is okay, I'll keep it there.
I think it's okay.
Yeah, perfect. Yes, and the first line, that is for installing this ppcharts package, if you haven't already done that. Next, we need to load the ppcharts package. But I'll start with an example using the blood pressure data, and then I'll start building a traditional eye chart using these data. So I'll assign these measurements to the BP object. And then I'll demonstrate how we would usually go about constructing a control chart using base R. We could simply say plot BP, and we would get this plot. We also would like to connect the dots with the lines, so we would ask R to plot of type O, that means overplotted. So here we have a primitive run chart. All we need now is of the three lines, the center line and the up and control limits. Let's start with the center line. We use the AB line function and add a horizontal line. So the mean blood pressure we put on this. We could use the same principle for calculating, for adding the lower and up control limits. But first, I'll assign this, the mean blood pressure, to a variable called CL. And then we can do the same with the upper and lower control limits. For those of you who are familiar with the eye chart, this would be a piece of cake. For those of you who are not, just hang in there. To calculate the standard deviation of an eye chart, we need first to calculate the moving ranges. The ranges, that is the pairwise differences between successive data points. And we can use the diff function to do that. And you can see here are the differences between the data points. What we are interested in is the absolute differences. So here, and we are interested in the mean absolute differences. So the average moving range, this parameter is 11. This parameter is important for calculating the standard deviation. We call this the average moving range assigned to a variable called AMR, and then we can calculate the standard deviation as AMR divided by a constant 1218. This is the standard deviation. And then we have the lower control limit, which is the center line minus 3 times the standard deviation. The upper control limit, center line plus 3 times the standard deviation. And then we can add all 3 lines to this plot. Lower control limit, center line, upper control limit. Now something's wrong here. Can you see that? We can't see the upper control limit because the plot, when we first plot data, there's not enough room to show the upper control limits, which we have down here. It's about 200. So we need to make room for this. We use the ylim argument. We need to close the blood pressure, lower control limit, upper control limit.
There's a typo, I think, there.
Range. Thanks. Yeah. That's it. So this is the basics of how we would construct a control chart using base R and no packages. So the idea is simple. We simply plot our data, and then we add these 3 lines. The center line is the mean of the data, and the upper and lower control limits are simply the center line plus and minus 3 times the standard deviation. The only thing that differs between control charts, different types of control charts, is how to calculate the standard deviation. So this is how we would do it using base R and nothing else. Now to PB charts. PB chart has a function called PBC, and then if we only use one argument, it will simply plot these data in a run chart. A run chart, as you remember, is a time chart, and a center line by default is the median of the values. If you want to plot it as a control chart, we supply an argument that we want the I chart, and this is the I prime chart. So here you have it, lower control limit, upper control limit, and this data point outside the lower control limit is highlighted using a red color and a somewhat larger data point. So this is the basic use of PBC to construct a control chart. We can add a lot of more information to this control chart. A title, let's label for the y-axis, and for the x-axis. Now see, here comes the titles. So this is the basic use of PBC, the PBC function from the PB charts package. Let's look at the help file. There are lots of arguments you can use to modify the chart, but the simplest use, the only mandatory argument is this x argument. If you only provide an x argument, that would be the data to be plotted. If you provide the numerator and the denominator argument and the x argument would be plotted along the x-axis. Let's show this in a demonstration. I'll show you a data set called on-time CT. These are data on patients with acute abdomen patients who were CT scanned within 3 hours after admission. So in this month, we had 25 cases, and 12 of these had a CT scan within 3 hours after admission. This is a classical case for a P chart, a proportion or percent chart. So let's try and plot that using the PP charts package. Also note that there's a data argument. If you have your data in a data frame, as in this case, you can tell PPC where the data are to be found. So let's create a run chart of proportions PPC, and then the first argument is the X argument, that is the month, and then we have the those that were scanned on time, and data from the on-time CT scan. This is a simple run chart. If we want to make that into an eye chart, we add the chart argument. So here we have, and here you can see the wavy control limits that we would expect from a P chart. These are proportions. We might want to show data as percentages. Then we simply add the Y% argument, and now you can see the Y-axis turns into percentages. Also, you may note that the upper control limit, this data point here, actually in the previous one, is slightly above 100%. When we use the Y% argument, we censor the Y-axis to 0 and 100 because percentages cannot be below and above 100, at least not for this type of data. Okay, any questions or comments so far? This is a basic use of PPC. For the rest of the presentation, we will go through some more examples. Any questions?
There's another question in Menti, but I think it's one that could wait till the end.
Okay. Then we'll move on. Then we'll look at some measurement data. This is a data set showing the average HbA1c value. And HbA1c is a measure of long-term blood glucose level. And these are for children visiting the regional diabetes clinic in the capital region of Denmark. And for these data, we only have the averages. I was not allowed to see the individual measurements, which I would have preferred, of course. Then I would have been able to make an X-bar chart of this. But I was given the averages and then the number of patients for each month. So this is a typical case for use of eye charts for aggregated measurement data. So I just have to remember the numerator is called average HbA1c and the denominator is called N. Let's make an eye chart. Sorry, let's make a run chart. Process behavior chart. This is a run chart of these data, and you can see here there's one data point that looks strange. It's very, very high. The average is about 60. Let's make it into a control chart. So this is a traditional eye chart. And this actually seems to be a special course. Now let's try and take the size of the numerator into account. So we will add the numerator as a third argument. Now something's wrong here.
No, do you mean the denominator, Jakob?
What do you say?
Are you going to use the denominator as a third argument?
The third argument is the denominator. The first argument, this argument is the numerator. The third argument is the denominator. Yes, yeah. Thank you. But something is wrong in this plot. Look at the y-axis. The values have changed from around 61 to around 0.3. And that is because the I prime chart always plots the numerator divided by the denominator. But in this case, the numerator has already been averaged. So to fix this, we need to multiply the numerator by the denominator before plotting. This is crazy. I know it's crazy, and I struggle to explain it to myself. But whenever data have been averaged, we need to multiply by the denominator in order to get the total HbA1c before we divide by the denominator. But now you can see this plot. We are the y-axis is back to the original scale, and this data point is no longer a special cause. So why is that? If we look at the data, we can see that there is one data point. It's with a very low denominator. Which one is it? This month has very few patients. It's in April. This one, April 2020. What happened in April 2020? I don't know about England, but in Denmark, this was the first month during lockdown, COVID lockdown, and very few patients visited the clinic in that month. So actually, this is not a special cause. This is just a random fluctuation because there are very few patients, and the I prime chart actually is able to discover that. I think this makes a good case for the I prime chart, that it is actually better than the original I chart because it discovers this. Okay, questions or comments? Anybody better at explaining this phenomenon? This is only for measurement data that have been averaged. Then we need to multiply by the denominator. Questions or comments?
There is another question which wasn't directly relating to what you're just talking about. So I'm still gonna sort of wait till the end. I did miss somebody who had their hand up earlier, and I don't know whether Andrew still has a question. Andrew Longdon, do you still have a question? Yes, he does. Andrew, go ahead.
Yeah, I think it mentioned earlier on in the notes that this assumes that all the readings are independent of each other. So am I right in thinking that the time interval between the readings doesn't matter for things like the systolic pressure?
We have the same assumptions for the I prime chart that for any other charts, that in principle the readings are independent. In fact, the control chart, and especially the run chart, is a test for independence. If there are any trends or shifts in data, it's a sign. It may be caused by data not being independent. Was that
sort of? I'm actually looking at doing some charts over HbA1c and blood pressures at the moment. But one of the things that I've got with the data is sometimes I've got multiple readings that are very close together.
Oh,
so
yes. You should, especially for diabetes. This is a special case, but for diabetes, you should only include one HbA1c measurement within a period of 3 months. Otherwise, these data may be connected.
Thank you very much.
Yes. Yeah. Great. I have a case here which is quite informative, but I think we are running short of time, so I might save this case for another time. Otherwise, you will have the code after this session. So let's look at some data that have multi-dimensions. These are data on mortality after bacteremia. So for each month, we have a number of bacteremia cases, and we have a number out of these cases, how many died. So again, this is a traditional proportion or percentage case we would normally plot in a p-chart. But we have a third dimension, that is the hospital dimension. There are 6 hospitals, and we want to compare the rates for these 6 hospitals. And PPC is able to do data that are faceted by one dimension. Look here. So we have the month. What's the numerator is death, denominator is cases. See, if I just do this, I'll get a crazy chart, because there are actually six hospitals in each month. So I will facet. I'll make a small multiples by hospital. Now, isn't this beautiful? These are faceted charts made with only base R, and each of these charts represents one hospital. You might notice that the lower control limits extend beyond 0. We can get rid of those by formatting the y-axis as percentages, as we did before. So now we have nice y-axis and we have percentages. PP charts is able to do small multiples faceted by one dimension. I have another package, QI charts 2, which can do faceting in 2 dimensions. But I have found over the years that is rarely useful. I almost never use it, and it's very complicated to program. So until further, PP charts will be able to do one-dimensional faceting of this. Okay, I think I will save this other case for later, and we could maybe have a discussion now. And if we have time at the end, or if some of you want to hang around, we could take some more cases afterwards. Is that okay with you?
That's okay with me. Yeah.
So
you have a good 10 minutes if you want to see it like that as well. So do what you'd like in that time.
Yeah, I'd like to hear if there are any questions, or if we can start a discussion now. Otherwise, I have plenty more examples to go through.
Okay, I'll just while we have that pause, and I'll just refer to, I'll just see what else is on Menti, just to make sure that we've captured these. So the first one we did talk about, and then we have two other comments here that you might want to think about.
Does the time interval between the measurements matter? As with all control charts, this matters. You need to have the subgroups need to be of the same kind. So if you have monthly measurements, you should not suddenly change to quarterly or weekly measurements. You should stick to monthly on the x-axis. Otherwise, you should do another chart and have the same units on the x-axis. That's important. Otherwise, it may be very confusing to look at. Yes, and then there's a. You mentioned the funnel plot. Actually, using faceted control charts, that's a very good alternative to funnel plots. Maybe not all of you know what a funnel plot is, but those who do, you'll see funnel plots is a control chart with a categorical x-axis. But you can use faceted plots as an alternative, and then you will have the best of both worlds. You will have the time, and you will also have the ability to compare between different units that may be regions or hospitals or clusters of whatever you're looking at. That's true. Yes.
Okay, I'm going to stop
So,
sharing that
so
screen.
my question now is: are we ready to have the I prime chart replace all the other charts that we are using? Some of you are SPC experts. What are you saying? And what do you say, Mohammed? You have an opinion, maybe?
Well, we've got hands up. Let people from the audience come in.
Okay.
Zoe, nice to see you.
Hello.
Hi.
There's one chart that I really like apart from all the other ones, which is time interval for rare events. I'm assuming this doesn't cover it, and we'll still
No.
need QI charts too, for example, your other package, to retain that.
Yeah, unless you want to use eye charts for time intervals between events. Some claim that you can do that, especially Don Wheeler, who's one of the very big experts on SPC. He says you can use eye charts for everything, and if you can use an eye chart, I guess the I prime chart is even better. In my experience, eye charts sent to, if you have a data that are where the distribution of data is very skewed, you will have too many false positive signals. But you're right, the I prime chart is not a substitute for the G chart and the T chart. That's right. And it's also not a substitute for the funnel plots.
No,
Good to have that clarified.
Thank you.
Mohammed, you were going to say something, I think, just before you. I know you put a couple of things in the chat. Too. Yeah.
I think if anybody's using the eye chart routinely, we would really welcome feedback on if they're happy to try out the eye prime chart. Given that the eye chart looks at variation between data points, the I prime chart considers variation between and within data points. It considers two sources of variability. So that key design feature makes it a superior choice by design, but in practice, how that pans out for people in the work they're doing, I think we would welcome further evaluation. But if you were to roll back the clock to when the eye chart was first introduced, it's an unusual chart because it doesn't consider the variation within subgroups, and so if it was designed in the way Taylor has just designed it, we would all be using his chart as standard. So it's come quite late in the development of SPC charts. So I think of it as one to explore further, but it is attractive in its design features. Jakob, do you want to add anything to that, or?
I agree with you that the I prime chart has a promise to replace the other common charts, but we need more experience. We need to find those corner cases that disrupts everything,
Yes.
or at least we need to not find any corner cases after a pretty long period of testing. But I haven't found anything not working with the I prime chart so far with the data I have at my disposal.
Yes. I think some of the other questions we've heard relate to rational sampling and sampling strategy, or relate to kind of general understanding of which charts to use and so on. They're not kind of central to the. I mean, they're important questions, but the I prime chart doesn't absolve one of addressing those questions. They're kind of remain methodological questions which have to be addressed. But I think the standard use case for saying what the plot the dots initiative was doing and so on, which is usually aggregate data presented monthly on board reports, is one common use. And so because denominators vary month to month, finding a way to bring in something which respects the denominators, and so it will end up showing wavy control limits. that point about wavy control limits is actually a good thing. I mean, you know, I don't think it creates any major barrier for decision makers to look at that.
Thank you. I think I've shared my screen again because there's been a couple of other comments. So and we have an offer here to trial. So someone wants to break it for you, which is so we have an offer. So Chris, actually, you've got your hand up as well. And you had it up before, and I didn't come to you. So Chris,
yeah, sure, thank you. Just to unify a couple of threads. So declared interest. I built the funnel plotter package with within and between adjustment for over dispersion and such like that. So I've got that interest there, but I'm very happy to use these because I found when I discovered the Laney P prime chart, that really opened up the use of things with different subgroup sizes. So I think it's really interesting that you're focusing on this and you're kind of tackling that problem, because a different subgroup size did make certain types of comparison really difficult. So yeah, I'm really keen to use these.
And Chris, we found that the I prime chart exactly matches the P prime and the U prime charts. When you apply this to the same data, you get the same results. The control limits are indistinguishable. So again, and some claim, not the least Laney claims that prime charts should replace non-prime charts. So that's another argument for having I prime charts replace everything so far. Yes.
That sounds really rational, because if a dispersion ratio is 0, you're not adding anything, are you? So yeah.
Exactly.
Yeah.
The comment about RTT data, I mean, so I don't think we've used it, Jakob. I don't think you've got access to waiting list data, but if whoever's made that comment and is interested in that data use case, then I'm sure you could reach out to Jakob or myself, but Jakob's really the one who's driving the package and so on. We are interested in collating use cases and identifying where things work okay, but where things fall apart. And so we can get some empirical evaluation.
Yes, I have looked at some waiting list data. Well, it depends on what type of indicator you're working with. If you're working with percentage of patients that are seen within a standard time, this would be a traditional proportion chart, and the I prime chart works, as we have seen, fine for those. If you could also plot the average waiting time in a given time period, and the I prime chart will do that as well as an alternative to the X bar chart. But again, we need more experience with these types of data, especially average times tend to be skewed. And I'm not sure what happens when you take very skewed data and put them in an I or an I prime chart.
So it needs testing, doesn't it? We need to find out how it behaves. Yeah. There's an interesting question here. So we've just got a couple of minutes to go, and I'm quite interested just to go to this one here, which is there a risk that this is harder for the customers to understand? So I suppose this is it's about how it's presented to the consumer.
Yeah, I think perhaps just to kind of invert the question a bit. So in a standard eye chart where the denominators are varying significantly or materially, is actually presenting a horizontal line for the control limits. That's misleading. So you know, somebody said analysis should be as simple as possible, but no simpler. So that oversimplifies a key feature of the data and can lead to essentially false signals, as Jakob just illustrated with the HbA1c data, for example. So I think the introduction of the waving limits will be a kind of it'll be a one-off learning exercise. In that you just have to explain once that this is reflecting varying denominators or varying area of opportunity, and then that should be it. So I think you get a more authentic view of the behavior of that process. But by doing so. So I don't think it's not a question of harder, it's one which is less likely to mislead and more likely to be informative.
Yeah.
I agree, and this is not a question of the I prime chart. This is a general question for all control charts that they might take some getting used to, for especially non-technical people, board members and managers and so on. So this is a general question for SPC in healthcare. Yes.
Yeah, absolutely. And I suppose my sort of, we have it 12 and I'm the one who's going to make us go over. So I don't know how I feel about that. But that relationship between the evidence and how you share it and the people who need to understand it to make a decision on it. So SPC charts, we've been kind of like pushing them out through the NHS, through the making data count sort of process. And I have a sort of an open question which you can't answer now really. Is the processes or the approaches that have been used so far have they been not misleading, but it's different, isn't it? So the techniques, the approaches have been slightly different because they're not what you've been talking about today. So the decisions based upon them might have been different had this been available sort of a few years ago. But anyway, that's sort of some sort of some thought processes that I need to sort of clarify in my own head, really, and as I understand the implications. But I would like to sort of finish it off today by saying thank you ever so much for sharing this with us. I've really enjoyed the session today, and it was delightfully different from the one we had a couple of weeks ago, which is the nature of our huddles. We have lots and lots of topics. If you want me to reach out to people, so we've already had Chris Maney offering for people to try this out with their own data, or if they've got some ideas on sort of applications and so on, I can do that afterwards. And yes, I'll share your GitHub with people afterwards as well. Maybe I know you've got one or two slides just to remind people what we talked about, and some of the code as well. That'd be fantastic. And I already want you to come back and give us an update in a few months. So I'll get back to you on that if that's okay. But I will just mention that you're going to be repeating this webinar or something similar next week at the NHSR for the NHSR community. So one or two people might rejoin with having reflected and want to ask some more questions. But on that note, I shall thank everybody for coming, and I'll thank you very much, Jakob, for joining us and presenting that to us. And I hope we'll be in time. We shall perfect it, and it will replace all the other charts with all the evidence to say that with confidence. Thank you, and thank you, Mohammed, obviously as well. Thank you, and I shall I'll close shop, and I'll see everybody in a couple of weeks, minus an hour approximately. So thank you. Bye bye. Okay, so there's a few people still on. So I will say I will go now, Jakob, and enjoy the rest of your day.
Yeah, I was just waiting for Mohammed. He said he wanted to.
Yeah, he did say that. He did say that. He'll probably reconnect. He might just ring you up. Okay.
Yeah.
Okay then. Bye bye.
Thank you. Bye bye.